name is Jay FUHRMAN, and I'm an earth scientist at the Joint Global Change Research Institute at the Pacific Northwest National Laboratory. To meet the aspirational 1.5 degrees Celsius goal of the Paris Agreement, we need to rapidly decline our emissions globally to net zero by around mid-century, and likely achieve net negative emissions by the end of this century. To do this, it's going to require large-scale carbon dioxide removal, or CDR. But the models that are being used to generate these mitigation scenarios have often relied mostly on bioenergy with carbon capture and storage, or BECCS, as well as to a lesser extent on afforestation and reforestation. But there are a number of other ways by which we humans might actually achieve CDR, or negative emissions, that include direct air capture, which is basically running giant factories to suck CO2 directly out of the air, as well as enhanced weathering, which would use alkaline materials on croplands and attempt to replicate geologic processes that would normally influence Earth's climate on a millennial to 10,000 year time scale. There's also biochar, which could similarly be deployed on cropland and use pyrolyzed biomass to store carbon in agricultural soils. And finally, there's technologies that could use electrochemical processes to actually strip dissolved CO2 from seawater, and these could potentially be paired with desalination. Policymakers and other stakeholders are interested in all of these carbon removal pathways, and while they've all been studied individually in isolation, they haven't all been evaluated together using the integrated assessment models, which can help inform how they might contribute alongside one another, as well as alongside other efforts that we know we need to be doing to reduce emissions. So we use the global change analysis model to understand these questions and also how they're going to affect global and regional energy, water, and land systems, so that the countries where they're going to be likely the most heavily deployed can start planning for that and also start planning to proactively manage any negative side effects. And we found that if these technologies are all contributing to removing carbon together, it can help reduce the risks associated with relying too heavily on any one carbon removal pathway or technology. And the CDR pathways that we added, like enhanced weathering, biochar, and direct ocean capture, all have potential co-benefits like improved agricultural yields, or the potential to use a carbon valuation mechanism to help finance hot and arid regions meeting their water needs while also removing some carbon. And so to be clear, we're basically starting from zero today. So we're projecting deployment of all of these technologies at scales that far exceed anything that we're seeing at present. But our results can help inform a more robust mitigation strategy, where if any one of them ends up not materializing, then we can have other technologies that can hopefully come in and fill that gap. And so we can mitigate the transition risk of, for example, devoting too much land to bioenergy crop cultivation, or such massive amounts of energy to direct air capture, while still reducing our emissions over time.